So we get to decide who was the first person that got sick. Okay? So I just have a random integer generator here, and our low value is 1, our high value is 9, and we have one poor person that got sick, and we're about to find out who they are. The person that got sick was number 3.
Are you kidding me?
Jack. Oh, I'm so sorry.
Ew.
So, Jack is very sick.
You're not sick.
Yeah, so you should have one.
That's why I'm getting it.
Okay, so this is our whole village right here, and unfortunately, number 3, aka Jack, got sick. So, would you guys agree with me that on day 0, one person got sick?
Mm-hmm.
So, what's going to happen here? The sickness is bad, but it has a very long latency period, and so he's pretty sick, but he just does not know it yet. He's very what's the word? He can spread, the sickness spreads. I'm losing. Say again? He's very contagious. He just doesn't know it yet. So he goes about his business the next day. And this next day, he interacts with a bunch of people, and he gets somebody else sick. So let's find out who got sick the next day. Number 9, Meg. Oh, so sorry.
Welcome to the party.
She's not dead, she's just sick, right? So after day 1, there are 2 people, number 3 and number 9, walking around that are sick. So this gets a little more interesting because now it's not just Jack who's sick walking around, it's Jack and Meg, both sick, walking around, talking to you. And so we're going to reset this, but instead of having one person walking around that's sick, it's going to be 2. So there's going to be 2 additional people that get sick here on this second day. Numbers 1, sorry Logan, and 8. Justin, I'm so sorry. Numbers 1 and 8 are also sick now. So after 2 days, there are a total of 4 sick people, correct? Okay. Third day, we don't have 1, we don't have 2, we don't have 4, or we do have 4, sorry, we have 1 or 2, we have 4 of these poor sick people walking around, and they still don't know that they're sick. Maybe at this point, Jack might be feeling some effects, but it's pretty mild. But we're still walking around, we're still contagious, spreading this around. And on that next day, number 6 to, oh my goodness, number 9, Meg got sick again somehow. I don't know how that works, but 6, who's 6? Peyton's sick, who's 2? Aiden is sick, Peyton and Aiden, and 7 is, all right, well, so after day 3, 7 people are sick. So let's see what happens in the next day. So now, instead of 4 people walking around, it is 7 people that are walking around sick. So we'll change this last number to 7. And who is it now? Well, 3 and 9 got sick twice on the same day, but they were already sick. 1 is sick. Oh my goodness, who's 4 and 5? You guys still didn't get sick. So I would say after day 4, we still have 7 people sick. So they must have a super strong immune system. We'll see what happens on day 5. It's really slow and awful sickness. I'm sorry. I'm sorry. Okay, so.
There goes 4.
Oh, Nick got sick?
No, I got sick.
Oh, Julia got sick. Okay, so number 4 got sick.
I said Nick would be the last one.
Okay, so you can see I only got time for room for just a couple more times on my table. So let's see if Nick, we're looking for number 5 here. Let's see if Nick gets sick on either of the next couple of days. So now we have 8 people. walking around sick. So is there oh my goodness. Nick continues on, not sick. So
There's a lesson
This is
from
basically how I
there.
imagine.
after 1 week, we're just gonna let this experiment go. So 7 days. Let's see if Nick can make the full duration of the week without getting sick. We're looking for a 5. Oh!
Yeah, loser.
Sorry, Nick. Finally, after a week, all 9 people are sick. So this is obviously random, and I have no way of knowing that 3 was going to get sick twice on the same day. I had no way of knowing that 7 was going to get sick twice on the last day after already getting sick. Totally random, right? You see any patterns emerging with the number of sick people in the days?
They slow down towards the end.
Slow down towards the end? Yes? What else?
It increased a lot in the middle and it was pretty slow on either ends.
Agreed. I don't know about slow on either end. Look at the first 3 days, right? Days 0, 1, and 2. What do you see for days 0, 1, and 2? Look at the outputs. What do you see? See it? They're doubling. And what do we call it when something doubles and then doubles? It's geometric or exponential growth. So for the first 3 days, days 0, 1, and 2, we can see exponential growth taking place, right? From 1 to 2 to 4. Isn't that, think about it, isn't that 2 to the 0, 2 to the 1, 2 to the 2? And we almost had, on day 3, didn't we almost have 2 to the 3? But not quite. Not quite, right? And then, clearly, as we got towards the end, the growth really slowed. So what I want to do is put this in a table. So, let's see here. So I'm going to go on my left column. I'm just going to take the table on the board, and I'm just going to put it up here in our table. So it was 1, 2, 4, 7, 7, 8, 8, and 9. Okay. That all make sense? Okay. So now I want to do a stat plot for this. And let's go, let's go to plot 1, and we'll turn plot 1 on. And list 1, list 2. Okay, this all looks good. And let's go zoom 9. Oh, there's another graph on there. Hang on. Let's get that out of there. We don't know what that graph is, and we don't want to know. There's what it is. Okay, so let's go back to our graph. Okay, so there's our data from our table that our poor little sick village generated. Any discernible patterns when we come look at the pattern in the table? Does anything else jump out to you with the graph?
Got a pretty good best fit on.
Got a pretty good best fit line. Okay, so let's try that. And by the way, what I'm about to do with the whole best fit line, we'll never officially do like on a test or a quiz or something. So if you find yourself on a quiz trying to do linear regression, just stop. Like we will never ever do that. But maybe in this little experiment it's good. So I'm going to store this in, I guess I could store it in Y1. Yeah. Okay, so we calculate this line of best fit. There it is. I go back to the graph. There's my line of best fit. Is that, what do you think as far as the line of best fit? Is that good, bad, medium, fair? Okay. So remember what we said, how the first 3 days seem to exhibit exponential growth? So could it be exponential? Let's try that. So I'll go back here and I'll say stat calc, and we're going to go power regression. Where did you go? Are you power? Or no, we could do exponential. Let's do exponential. I think that'll be fine. Okay, so same thing. I'm going to store this in Y2. alpha trace y2. And so here is what it's telling us for that. I'll graph this. Hopefully this will be a different color. Oh yeah, so the blue is linear regression. The red is exponential regression. So it's, a to the x, something times a to the x. Of those two, which seems to be the better fit? Linear seems to be a little better fit, you think? Got some pretty significant outliers for both, though, don't we? What could we do? Cubic, all right.
I would tell you.
Okay, so let's do that. So I'll go stat, calc, and cubic is 6. So there's that. I'll store this one in y3. Okay, so let's see what happens here. There's that. Now I'm going to graph. Okay, this will be interesting. So this is a black graph for the cubic. What do y'all think?
That's pretty good.
Reasonably decent, isn't it? I mean, somebody could argue that that's better. The one thing you could argue, however, is like for the first 3 or 4 data points, doesn't it appear that my data points are concave up? Yeah. And for this whole interval, that black graph is concave down. I mean, as far as the connecting of the dots goes, that black graph is pretty good, right? We're just trying to connect dots. Can you think of anything else? Oh, logistic. He's got a look on his face, and I don't know. Let's see how this looks. So, stat, calc, logistic is like way down there somewhere. Logistic is right there. So, golly, well, this is going to be y4, isn't it? I think I already did 3 of them. So, y4. Calculate. Does the result of this, once the result shows up, the thing about it is, yeah, it's like, whoa. Oh, there we go. Yeah, all right.
You know the good old C over emphasis.
This is actually, you guys remember from a couple days ago, this is actually a different version of mice minus Katie. So, okay, so graph, hopefully this will be a different color. It's pink, yes. Okay, so we've got all these different colors. Oh my goodness, it hit the first 3 points.
Does it turn over? Yeah, it does.
Oh my goodness. It went right between those two. And it hit that one, it looks like, yeah.
Oh my
And
God.
then it perfectly split those two about, or almost hit that one. Whoa.
That graph will really get you going.
Interesting. It's like you guys are cheering for the graph. I love it.
It's like a racehorse.
So, you guys agree that the pink graph is a pretty nice
Do we,
approximation? Can we what?
We go to the other three?
Sure, let's get rid of the other. So, why, Aiden, would you pick logistic as your proposed fit?
Because it's x-rays of the beginning within the second factor. We have definitely replace those way out.
So, in our little village experiment here, what was the factor that kind of limited the growth? Right. So, how many people could have gotten sick? 90, right? So, what do we call it? What's the term for that? That living number? Remember this? It's been a couple days for sure.
Population.
Therefore, yeah, the limit is based on how many people there are.
Carrying capacity.
Carrying capacity. Yeah.
It took me a minute.
So, yeah, so our carrying capacity was 9. So what if I went back here and I said, if I put in another equation and I just said for that other equation, y equals 9, so a horizontal line at 9. So this will be in green. Does it look to you like maybe that green line would be related to the pink graph in some way? This would be a horizontal asymptote. That's right.
Nice.
The reason why the pink graph could never jump up above that is because only 9 of you could have gotten sick. Right? We can't say, oh, one day there was 11 of you sick, because there was only 9 of you. That's the max. That's the carrying capacity. Some other things we're talking about here, this pink graph is very characteristic of logistic growth. Right? If you see logistic growth, any kind of pattern like that, the graph will look in some form or fashion like this pink graph. It'll get real steep, and it'll start to get less steep, and then it'll start to really flatten out as time goes on. What if I replaced this with, like, I don't know, what if I just said n of t, where n stood for the number of people that were sick? And what if I gave you a couple of questions? What if it was, the limit is t goes to infinity of n of t? What would you all say that would have to be?
9.
It would have to be 9, right? As we go to the far right edge of the graph, our pink graph would be getting closer and closer to 9. Agree with that. And maybe a follow-up question would be this. Limit as t heads towards infinity of n prime of t. Any ideas on what that might be?
0.
0, right? Because the further you go out there, isn't the graph just getting flatter and flatter and flatter and trying to, like, basically level off, right? So I would say that our rate of growth would be approaching 0 as t goes towards infinity. Is it going to hit 9? So this is where, like, the real world practice and the theoretical modeling sometimes have a disconnect, because, you know, that pink graph won't ever actually hit 9. But we know in the real world it's very possible for all 9 people to get sick, right? And so, again, we would say that this pink graph is a model for the population. It's not a perfect, exact representation. It would just be the best model that we could come up with. Yeah. And when you start to think about really huge populations, like what if we're talking about an epidemic, like a pandemic of sickness over, you know, hundreds of millions of people, would we be for sure that all hundreds of millions would actually get sick? No, there's always going to be some outlier. It was almost Nick, who just has some weird immune thing where they just don't get sick with that particular illness, right? I mean, there are some outliers out there, right? And so even in that case, I think we probably could say there are going to be a few people at least that would not get sick. And so, yeah, the difference between theoretical and actual practice can be different, for sure. A couple of other things to point out to you here. I'll do this on the screen. Y'all can see that clearly the pink graph at places is concave up, and then other places is concave down. So there's clearly an inflection point, right, because of that. Where would the inflection point be? How would you describe that?
N double prime equals 0.
Okay, when n double prime equals 0, n double prime would be changing signs, right? And Sam, what did you say? 4 point. When what is 4.5?
Oh, it's 50%.
So is it when t equals 4.5 or when n is 4.5?
N of t is
There we go.
m over 2.
So you know what? Why don't I do this? I'll graph that as well. Let's see how this works out. If n equaled 4.5, oops, well, we'll just put it there. This will be a black graph. N equals 4.5. Does that look about where that pink graph goes from concave up to concave down?
Heck yeah, it does.
It's also where that pink graph is steepest, right? Steep as it's going to get. It's looking really exponential, right? I'm looking at this part right here and I'm thinking, boy, this really looks exponential through here. And then I start to look at this part and I think, whoa, not so exponential anymore. It's that place where it goes from looking pretty exponential to maybe not as much. That's your inflection point. It's a good description. Pretty poor as far as being rigorous. Yeah, certainly where the graph is steepest, the pink graph is steepest, would be where you have that inflection point, and that is halfway to the carrying capacity. So sometimes people get a little confused and they think, well, when t was 0, number of people was 1, and so they think that will affect this inflection point. The inflection point will always happen when you're halfway to the carrying capacity, no matter where you started. No matter where you started. Okay. It's a good intro. Does it make sense? Okay, awesome. Very good. Any questions? Okay, cool. Well, let's do a few of these guys from our packet. I want to just review this part. We've kind of reviewed a lot of this. The one thing we have not really reviewed is the differential equation version of this. You all just saw the solution curve version. Let's make sure that we filled this out before. I just want to make sure that we have said it again because this is brand new, I think, to everybody. This is your differential equation for logistic growth. What does P stand for?
Population.
Population, yeah, this stands for the number of people that are sick or have heard the rumor, or the number of bunnies in the field, whatever. So you should have most of this filled out. You should. K is going to be your constant. This is going to describe essentially how fast the sickness is spreading. It's going to affect the rate of that. And then M, what does M stand for?
Carrying capacity.
Carrying capacity, yeah. So carrying capacity is quite literally, it's the maximum number of people that could get sick, or the maximum number of bunnies that a field could hold, or the maximum number of moose in a national park, right? You can't just drop 500,000 moose into a national park and expect it all to be good, right? They're probably not going to have enough territory, and some of them are going to die, right? There's going to be some kind of a carrying capacity. And by the way, we typically are going to look at this as logistic growth, but there is such a thing as logistic decay. And that would be the example I just gave you. Like, let's say that a national park could only support like 1,000 moose just because of the terrain and such, the resources that they would have. If we decided to introduce 3,000 moose into the national park, they would not logistically grow. They would actually logistically decay back down towards the carrying capacity. Does that make sense?
So it just always kind of, the trend is always towards that M.
Exactly. Whether you somehow started above, or more likely you started below. And so since it's a more likely case that we'd start below and grow towards it, we'll typically look at logistic growth as the topic.
So then can we say any time that we have a logistic growth, it could be a fair assumption to say that the limit as that function approaches infinity is always going to be M?
Going to be the carrying capacity, yes sir. Yep, just like this. So a great example would be, say Valor. Like they say that our carrying capacity for our current facilities is 1,200. Like somehow they've come up with that number, and we're like at 1,170 something, right? I think this year, something along those lines. What if next year, and I don't know why they would do this, but what if they accepted a ton of people and our population got up to like 1,300, let's just say. And let's say that 1,200 really, honest to God, was the carrying capacity. Like they somehow knew that. What would happen over the next year or two?
Students would transfer.
We'd see a decline, right? Some of the reasons would be, well, the halls are even more crowded than they were before. I have to wait in lunch line forever now. Or the services that I'm looking to get, I just can't seem to get those. Not enough of this, too much of that. And people would say, well, gosh, I just don't think this is worth it. And we would decline back towards the carrying capacity until everybody was happier. Does that make sense? And so you can get decay with logistic behavior as well. Okay, so I do want to review real quick because we just touched on this at the very end last time. The solution to that differential equation, which is dV dt equals Kp times 1 minus P over M, you're going to want to recognize that. You're going to want to see that and be like, that's logistic growth. And there's the potential there for something to look a lot like logistic growth, but not actually be it. So we'll focus on that here today for sure, and in the coming days. But the solution to that logistic differential equation is this right here, P equals M over 1 plus CE to the negative KT. As we talked about before, I think of this as mice minus KD, as just a mnemonic device to help you remember it. If you can think of a better way that helps you, then you just do that, and I'm okay with that. Somehow when I think I came up with this like 7 years ago, and you still know who Katy Perry is, right? Man, she's actually had some staying power. She actually is still in pop culture after 7-8 years. Impressive. That's why I question it. I feel like she might be fading a little bit.
Her is from like 7 years ago.
She's on American
Maybe.
Idol, did you know that?
Yeah.
She's on one of those shows. Is it American Idol or The Voice or something?
American Idol.
Okay. Well, maybe that's part of the reason that you still know who she is.
Logistic decay for population.
There you go, yeah. Her population reached a peak, and now it's like down to, and then it'll just be a certain population that's sticking with her. I like that. That's good. So you'll always be given some information to help you figure out what the C and the K are. You're going to have some data points where maybe some scientist has gone in and measured something, or there's been a reporting out of some data that would allow you to actually figure out what the C and the K would be. Okay, so let's try some stuff. So our first example is a national park example. So this says 10 grizzly bears were introduced to a national park 10 years ago. A couple of 10s there. There are 23 bears in the park at present time. And somehow some researchers have figured out that the park can support a maximum of 100 bears. Assuming a logistic growth model, when will the bear population reach 50? Okay, so you've read it. I read it out loud to you. How do you feel? Do you think this is something that you could start to tackle, or do you need some guidance on how to start? Where are we at?
I feel okay.
Okay, well, I'll give you a few minutes to just sort of use some of these things, see what happens, and then I'll certainly try to help you at the end. Yeah.
C is the initial value, right? The initial.
So you want to be really careful. So in logistic growth, no.
Okay.
It's going to be related to that for sure. But it's not going to be that exact same number. You'll see, like if you start to explore with this, you'll see it's I think pretty much never, unless, I think if you start off with 0 population, then I believe they would be the same. But we'll rarely, if ever, start off with it because somebody had to get sick first. Somebody had to hear the
Yeah.
rumor first. There had to be at least 2 bears, right, in order for the population to grow. So we'll typically won't start off with 0.
Okay.
Yeah.
So how?
Happy to answer questions. I want you to have the chance to try this on your own, knowing that you might get a little lost. I don't know, but I want you to. It'd be cool if you could at least get some stuff going and have some idea of what you're doing. If you're having a hard time, think back to the two big pieces of information that I showed to you are the differential equation for logistic growth and then the solution curve for logistic growth. So think about if either one of those could be used here and what you could do to use it. How are K and P different? K is not the amount present. K is a constant that governs how fast the growth is. So like if K is a bigger number, it'll be super steep at the start. If K is a smaller number, it'll be less steep at the start. So K is going to be some constant like 5 or negative, or not negative, but or 1/2 or something. P is a variable. P is the population that has heard the rumor, the population of the grizzlies, population that's sick, the number of people or beings that have been affected by the situation.
No way.
Am I gonna weird? It's not whack.
That is kind of like.
You're trying to find when. This is a time question. Ultimately, yeah, trying to find the time when P is 50. And by the way, I actually, this little experiment we did with the population and getting sick and everything, way back on a day in the life, which is our like back to school parent night thing that we do here. I actually did this with your parents. I did an abbreviated version because we only had 10 minutes, so we did a very abbreviated version. But we got to the graph and everything, and everybody's like, "Oh wow, cool graph," and we talked about some of the significance of it. And then Sam's dad, who is a doctor, with cancer, right, deals with cancer. He was looking at it, and he's like, "That looks a lot like a sigmoid curve." And he's like, "Is this the same?" He asked me, he's like, "Is this the same as a sigmoid curve?" I was like, "I don't know, I've never heard of that." So I looked it up, and it is. It's the same It's the exact same thing. So a sigmoid curve is a logistic growth curve in which the base on the little exponential is e, and the starting population is 1. It has like a very specific form of a logistic growth curve, and they use the sigmoid curve to figure out how much cancer medicine to administer. Because cancer medicine like kills cancer cells, but it also kills good cells too, right? And so they use the sigmoid curve to figure out how much medicine should we actually give the patient so that we don't kill them, but we do our best to kill the cancer. And so it's kind of an interesting little thing for me to look up, because he was like, I think it looks the same. I thought, it sounds like it's the same, and indeed it is. So it's kind of a cool little connection there. So it's even more than just rumors, right? It could even be describing how do we deal with this person's cancer. So I learned a little something there too, but a little research, because Sam's dad was like, what about this? Does this make sense? Yeah, I guess it does.
That sigmoid curve is also used in neural networking when you're programming it. That's the function that you use to determine what's decision you make between the choices.
Interesting.
And
That did not come up in my research. Now, see, there's one more thing for me to think about. Cool. Interesting.
Not myself a massive equation. Star Trek Bibles.
So as you all know, maybe you're wrapping up this or coming to a conclusion. You'll know that our Chapter 8, which is Unit 4 test, is tomorrow. And I'm sure you're all aware of the possibility of, in spite of how it looks out there, we're supposed to get a lot of snow tonight.
Yeah, it's supposed to snow from 7 to 7.
Moving tomorrow.
Right. So,
I
so
saw it. Oh my god, that would be
FYI, as you know, like we don't have time to say, hey, there was a snow day, so let's just pretend like that day never existed. If we did, we'd have to go to school like one day into Christmas break or something, right? And so if that happens to be the case, well, obviously we'll have to move the test to a different day. But be on the lookout. I would probably have a little activity for you with logistic growth for you to work on. Just so you know, snow days, like, it doesn't mean that we don't exist, and it doesn't mean that time doesn't keep moving forward. So just be on the lookout. I have no idea. It looks like it's actually going to, it's not freezing out there right now, so there's a possibility it could snow 6 inches and all of it melts. Or not.
That's not what that.
We just don't know. So, but please don't be that person who, when I see you on Friday, you're like, what? You sent an email to me with a link to something? What is this email you speak of, Mr. Anderson? I never heard it. Like, you will be getting something from me if this snow day does indeed happen. I'll just be sending you something to continue to ponder, so that when you come back on Friday, you won't have that look on your face like, what? It's been like a millennia since I've been to school. I don't know what you're talking about. Okay. So oftentimes, like, the second day is always like the worst day, right? Because then that's when the snow kind of melted, and now it's frozen, and now it's insanely icy. So who knows?
C equals
It's senior night.
Please go.
Senior night.
To what, volleyball?
football on
For
Friday.
volleyball?
The football.
Yes, for volleyball.
That,
Okay, here we go.
I got you.
Did you guys discover which form is the better form? Should we use the differential equation form? Should we use the solution curve form? What did you find was the way to
I
go?
used the solution.
I think the solution curve, based on the information, the solution curve is definitely the way to go. I agree. So hopefully you could remember that for the solution curve, P is equal to mice.
Is that your T? I messed something up.
There's mice, right? And then minus Katie is right there. And of all the things that we know, which one is the easiest to just immediately plug in?
Well, we always use that.
0.
M, 100.
M. I think it's M.
Well, we always use the minus.
If it's logistic growth and you're going to be using the solution curve version, it's this. Say again?
How do we know to use the solution?
Oftentimes it'll just say it's a logistic growth pattern, like this one. It says, assuming, oops, I missed.
Oh, okay.
Assuming a logistic growth model, so
Got it.
that would be your big hint for sure. Other times the big hint might be they'll give you the differential equation. And they won't call it logistic, but they would rely on you seeing, okay, P equals, or dPdt equals Kp times 1 minus P over M. That's logistic growth. They would be assumed that you would recognize that and say, oh, okay, we're dealing with logistic growth, therefore, whatever, right? I need to do what I need to do. But Sam, I do agree with you that M, the carrying capacity is 100, right? We're told that the maximum number of bears that could live in this national park is 100. So M has to be 100. The C and the K, like the P and the T are variables. They're just going to be P and T, just like in y equals mx plus b, the y and the x are just variables. Here, the P and the T in the end will just be variables. So the C and the K are really what we're going for. Did you guys see any information that would help us figure out? I mean, Jack shouted 0 out a second ago, which I agree 0 is important. What do you see, Logan?
Well, you're given 2 points for P and T, and that's
Yep.
0 and 10, and then 10 and 23.
Yeah. Isn't this our 0, 10 is right here. 10 grizzly bears were introduced 10 years ago. So that would be our T equals 0, right? Okay. So that's 0, 10. So I'd start off, I'm going to try to find C or K right here. So I'd say population is 10. And time was 0. So that would just be CE to the 0, wouldn't it? All right. So 10 equals 100 over 1 plus C. You cross multiply, you get 10 plus 10C equals 100. You subtract 10 and divide by 10. I got 9 for my C. 90 divided by 10. Okay, so then I'm almost there. I'd say now P is equal to 100 over 1 plus 9e to the negative kt. Except now I've got Logan's other data point, the 23 you said?
10 and 23, yeah.
Yeah, so 23 bears now. So that would go with 10 comma 23. Meg, what's your question? Sorry, I didn't see your hand.
No, you're good. So I get like y at 0 because t is 0, but what is k? Like, how do you find k?
We're about to. So in order for so if you think about it like this, with a differential equation or just a population like a solution curve here, if you have 2 unknowns, you need to have 2 equations. And I've got one equation based on 10 years ago. I'm going to be able to come up with a different equation based on now. And that's what Logan's talking about. So 10 years into this, there's 23 bears. So that's now. We're 10 years into it, and there's 23 bears. So I can now say, all right, so population is now 23. Used to be 10, now it's 23. Equals 100 over 1 plus 9e to the negative k times 10. And obviously now this equation only has the one unknown. So I can do a little bit of algebraic work and come up with a good answer for the k. Does this make sense, Meg? So, we'd cross multiply again, and I'm hoping that at least one person worked the details here.
K without the negative equals 0.099.
0.099. And I'm assuming there's probably some dots on there. You'd want to keep those dots. You all okay with solving that, or do you need to see the steps? Okay, I'll show you. I'll do my best with time. Okay, so it'd be 23 parentheses 1 plus 9e to the negative 10k equals 100. I do that by cross multiplication. I would then divide by 23. And I would subtract 1. And then I would divide by 9. So e to the negative 10k equals 100. Well, I guess I could just do 100 23rds minus 23 23rds. So it'd be, 77 23rds. Divided by 9. And then I do the ln of that. And then I would divide by I'd divide by negative 10. So I'd get k equals the natural log of 77 over 23 over 9 divided by negative 10. And according to Jack, that is approximately 0.099. ... Bless you. Clearly calculator time once you get down to that stage. Okay, So now that we know our C and our K, we can actually answer the question. Let me switch colors here. So I've got, for my differential, or for my solution curve, I've got P equals 100 over 1 plus 9e to the negative 0.099t. And the question says, when will the bear population reach 50? So it's when P is 50. So P equals 100 over 1 plus 9e to the negative 0.099 ... t. So really we'd follow a very similar process like we did to solve for the K value, right? We'd cross multiply, do some division, and do a logarithm, a little more subtraction and division. We'd eventually get a T value. Did anybody figure out what the T value is?
22.219 years.
And I saw Peyton mouthing the same number. Okay. So approximately 22.219 years. This is how long it would take. Did anybody notice that the 50 happened to be halfway to the carrying capacity? Right?
Yeah.
Carrying capacity is 100. So we could say that the inflection point of the curve also happens here at this 22.219 years time. And we've answered the question, 22 years. So if it's now 10 years, so it'd be approximately 12 more years, right? 12 more years from right now. Okay, what do you think? Any questions? Okay, well, let's do another one here. Our other example is here. Example number 2.
I like this problem.
So this is a great place for us to eventually finish our class. I don't think we'll be able to answer every single question in our class. My plan is maybe to, assuming we don't have a snow day and that things don't get messed up, my plan would be on Friday to wrap this one up. I'll read it out loud here to you. It says, the rate at which a rumor spreads through a high school of 2,000 students can be modeled by that differential equation where P is the number of students who have heard the rumor T hours after 9 a.m. So I'll tell you what, let's do A real quick. Yeah, let's do A real quick. So what would be your quick answer to A?
1,000.
1,000, right? And where are you getting that from?
Well, it's the inflection point, which means that if we're talking back to our derivative tests, that's when the slope or dp dt or whatever it is changes from increasing to decreasing, and anywhere it changes from increasing to decreasing, there's a maximum.
There's a what?
A maximum, a relative max.
For sure. And so how did you know specifically 1,000?
Because the inflection point of any logistic growth model is at half the carrying capacity.
True. Very true. Do you remember how we had this differential equation that I gave to you a couple days ago, and then we talked briefly about it earlier today? Did you notice how the differential equation that you see in this particular question kind of sort of looks the same, but it's not exactly the same? So, yeah, factor out a P and factor out a 6. So let's see what happens if we do that. Be dp dt equals 6p. Now, why specifically would you factor out 6p? Yeah, the first number has to be 1, and that's the only way you can get a 6p to be a 1 is to divide it by 6p. So that would equal, well, p squared, if you factor it out p, there's a p left over. What's 0.003 divided by 6? It's some crazy decimal, right? Or not crazy. On the left side of your calculator, there's a button that says x to the negative 1. You ever used this before? It'll automatically take whatever you have in your calculator and flip it, like do its reciprocal. So go ahead and do that 0.003 divided by 6, get a result, and then flip it, and what do you get? 2,000. Yeah, 1 over 2,000. So it's P over 2,000. Very useful button. So you could actually...
We could just math bracket.
Yeah.
I suppose. That's weak sauce, I think, but whatever. Somebody from 30 years ago would tell me that calculators are weak, but, you know, whatever. Anyhow, so you can maybe see how this logistic differential equation really does go with a carrying capacity of 2,000 which would then mean 1,000 is when we are halfway to the carrying capacity, which would be when the rumor is actually spreading the fastest. So I look at a question like this, like let's say it was a multiple choice and it just said, for what population is the rumor spreading the fastest? If you just know that when you're halfway to the carrying capacity, you hit that magical point of steepest, that question should take you like 5 seconds at the most, however long it takes you to fill in the bubble, right? So useful thing to know for sure. I think we'll do B, C, and D, not tomorrow, but whenever it is that we have a regular class, but don't pack up yet. This question, I'm just going to plant this seed in your mind. This question is kind of a launching point for a project that I like to try to do every year. And some years it seems to happen really great. Other years it seems to not work so great. And that is to spread our own rumor. Done this before. A couple times it's worked awesome. A couple times it's not worked so well. So the two keys to making this work. Any rumor that we try to spread has to have two characteristics. Number one, it's got to be scandalous enough that people would actually repeat it. And number two, it can't get someone fired or put in jail. It's got to have those two characteristics. Okay? So it's kind of a narrow path. Can I tell you the very best rumor of all time that we've ever spread? This was, listen now, this might give you some creative thoughts. This was like 7 years ago, I want to say, or maybe 6 years ago. The very, very best one was, I spread the rumor that Tim Tebow was going to come speak in chapel.
That's well done.
6 years ago, 7 years ago, whenever that was,
He was still relevant.
super popular, relevant, people freaked out. And the only casualty of the whole deal was the poor person who actually did speak in chapel the next week, because everyone was like, "What? Wait, I heard it was Tim Tebow." But that rumor was incredibly good. Yes. So this was back before they even had a little scanner card thing. So, was what?
It can't be true.
Well, no, it could be true. It could be true, but again, it has to be scandalous enough to be repeated, but not get someone in serious trouble, right? The other thing that's got to be considered is the collection method. And I've got a couple of ideas on that, but as we kind of work through this, and we don't have to do it right now, we could even do it in the springtime or something.
No, I want to do it as soon as possible.
We can just design our own little rumor and ways of collecting the data and that kind of thing. I'm open to possibilities. So we'll talk about that again probably on Friday, assuming we don't have a snow day, and we'll just kind of take it from there. So have a great rest of your day.
Just